for advanced topics in artificial intelligence for intelligence systems. And I'm Zia. I work in Robin Group with Charles and others, and Jim is our leader over there. So I guess you already learned about or already heard about the deep learning things a little bit before. Bruno gave a little bit details about that. So today I'm going to discuss some kind of dimension reduction and also feature extraction, mostly from image processing. But as you know that image is also kind of signals. So it's basically 2D signals. So you can also apply it to other signal processing works. So at the end of the presentation, I will show you some demos, okay, so that you can get a little interest about computer vision related things. And later on, if you are more interested, you can stop by my office or you can ask me. And I will help you out how to implement this mostly convolutional neural network things, okay? So let's start with the most basic feature extraction or dimension reduction things. That's basically principal component analysis. I guess you must have heard about that thing. And you know that data can be organized in different ways, and data can be clustered in different ways. So and data can be of different dimensions. So when data is very long dimensional, then it's sometimes it's necessary to reduce the dimension without losing much information. So principal component analysis is such a tool or such a basic thing that's mostly used and very popular in image processing and also signal processing tasks to reduce the dimension and without losing much information. Okay? So how can we apply principal component analysis, or what's the advantage of using principal component analysis? We can see here that it's basically when we apply PCA, then we find out some basis from the data so that we can use those basis information or basis to reconstruct the original signal, and we can see that, and we can compare with the original data that there is no much loss. And a good thing with the image processing is that when you reconstruct the image, you can visually see that how much or how it is. So we can see some examples later. So it's basically used for various purposes and mostly used for dimension reduction, and also it can be used for feature extraction sometimes in image processing. So what can we do? Basically, what's this feature analysis and feature space things? Basically, when we have some data that's in a normal dimension, okay? So PCA will find out another space. For example, we have here a laptop, and my original slide is in the laptop, right? Now, to see over here, we are projecting, okay, using this projector. So the feature space analysis is like that. We have data in one space, so we will take that and project into another space and see what kind of advantage we can get. You can see over here, here is the data in 2D plot. And when you look at the data, you can see here that there can be two most directions where the data can be varied. So in that case, we can see that if we can get two principal components, and we can apply on the two principal components our original data. So when you get some data, you can analyze this. You can analyze data with principal component analysis and try to find out the principal components, the necessary principal components. How will we find that? We can see that later on. So it's basically take data in one space and project into another space and see how it can help us. And it's mostly the main concept is here the covariance of data. And find out the eigenvectors in that covariance matrix to find out the most important directions. So there are some examples over here. You can see here that here also two direction is very important. Okay, you can see here two directions. So it's basically these two directions, these two dimensions, that those will be our feature space. That means you can see here that if we go back, this is our original coordinate system, right? Okay, but when we find out the principal components, then this will be our transformed space. Do you understand? We have one space, then we find out another space, then project data on that space. That will become our that coordinate system. Okay? So here, the original data was here in the coordinate system. Now, when we find out the principal components, then we project onto that, then this will become our transformed coordinate system. That's basically what we do. That's basically projection over here in principal component analysis. So, if I go a little bit more, I think, there. It means that if I can draw a little bit over here, I will go a little bit fast later, but first, as it's the beginning, so I'm just, so here we have got these things, okay? And then we get this direction and this direction, right? Now when we project that, then data will become like this, in that space. Originally it was like that when we projected, so that's, that will be clustered like this. So it's basically, and one more important concept is that one principal component is orthogonal to another principal component. Okay? So it's always 90 degrees from each other. And not necessarily there will be two directions. There can be more and more. Okay? It's based on your data. How is that? So it's basically finding out the most important direction in the data that you can consider to apply, and the number of directions will represent the number of dimensions. And how can we find out the most important direction? That will be represented by eigenvalues. So it's basically eigenvalue decomposition problem. And you may have heard about this eigenvalue decomposition in mathematics, that eigenvalue and eigenvectors. So that's that basic mathematical formula you can apply. And PCA is, I think, almost available in most of the languages, programming languages, Python, and it's very available. Okay, and in MATLAB you can easily just type PCA, and that will be available over there, and it will find out the principal components, I mean eigenvectors and also eigenvalues. Now, what would this eigenvalue and eigenvectors represent? Then we can see, and how will we find it. So you can see here that there are 100 by 100 size image. So basically, as I said, that the same thing can be applied in the signal processing as well. So when we get a time domain signal in anywhere, from any sensor, it can be music or it can be accelerometer, it can be gyro, whatever, okay? That's basically just a dimensional, right? Time sequential data. So remember that when you apply PCA, first of all convert that into the one dimensional, I mean in one row, just like a normal signal. Then you can apply, you can just again rearrange image from that signal, and then you can see how it happens. So it's basically available in most of the signal processing tasks, but when you apply on images, then you can also represent that similar way, okay? And when you find out the image, then you can also just, from the principal components, you can generate the image, the way you generated the signal. Am I clear? Kind of? Okay. So you can see some faces over here. And you can see here that And first of all, we need to do that, subtract the mean. Okay? So this is the mean image. Okay? We need to get it out and then find out some eigenvectors. These are top eigenvectors. Okay? And you can see that this is just like an average images. Okay? So these are the bases. Combination of these things, we can build the original image. So that means when we have this, okay, we apply principal component analysis on these things. Then we get the eigenvectors, and those eigenvectors we can rearrange as an image. For example, these all are 100 by 100. Okay, 100 pixels by 100 pixels. So when we convert it to the one row, then it will be kind of 100,000. Okay, 1 by 100,000, right? Okay, what I'm saying that this is an image. Okay, these are all rows, right? So we take first row, and then second row, and then third row like that. So this is 100 by 100. Okay, then we will convert it to 1 by 10,000. Right? So each image is converted like this. So if you have 50 images, then this will become 50 by 10,000. Okay? 50 rows like that. And you apply the eigenvalue decomposition, then you can get eigenvectors from there. And before that, you need to find out the mean and find out the covariance. Okay? So the steps, I'm just coming that later on. What should be the sequential steps of that? So when we apply principal component analysis on some images, we can get some principal components, that is bases. And those principal components basically orthogonal to each other. Okay, so you can see that. So a base is basically linear combination of these bases and also their coordinates. I mean coefficients. So, and we can reconstruct the base. If you consider all the bases, principal components, you can reconstruct the original image. But if we consider all the bases, that means we cannot do dimension reduction. We will find out the most important principal components. Then we will project onto that, then the dimension reduction will be done. Otherwise, it will not be done. So you can see here that if we have this, if we consider only 4 principal components from those 100 images, okay? If we consider only 4 principal components, 4 basis images, and find out the combination of, multiplication and combination of those, then we can reconstruct the original image. So you can see here, if we consider only 4, we can generate the original image. But this is not looking like the original face, right? Okay? That means too much information is lost if we consider only 4 bases. If we consider 200, then we can see here that, okay, almost, okay? And then if we consider 400, then almost the original image. So that's the main challenge. And how many principal components we should consider, that depends on the eigenvalues. Okay? If we see one example, you can understand that how to apply this principal component on that. For example, these are the human body sealers. Okay? Then how can we apply here principal component analysis? We can convert each image to a single row. So all converted to rows, okay? Then subtract mean from every row, okay? And find out the covariance and apply eigenvalue decomposition on the covariance matrix. And then use that for reconstruction. So you can see here that these are eigenvalues when we apply the eigenvalue decomposition on the covariance matrix. This is really interesting in a way that you can see here that the first one has very high value. The second one, low. So, and you can see here that around more than 40, it's almost 0, right? Okay. That means if you consider up to 40 first principal components, and you reconstruct the image, then you will not lose much information. That means if the images are, if this image is 1 by, like this, if the original image is 50 by 50, okay, if we have like this, okay, then if we consider here 40 bases, so that will be 40 by 2500, okay, that is 40 basis images in the principal components. And when we project this one to here, then this will become transpose, okay, so this will become 2500 by 440. So when we multiply that, that will become 1 by 40. So you can see here, from 2500 dimension, it will become only 40 dimension. Okay? And if we reconstruct the data, we will not lose much information. So that's how we can apply principal component analysis on any signal. If we have some collection of signal data, okay, either it can be from images, either it can be from another sensor, so we can apply principal component analysis. How? We can subtract the mean and we can find out the covariances and just apply eigenvalue decomposition on the covariance matrix. And from that eigenvalue decomposition, first eigenvector is the most important, then second one is the second most important. Okay, and how would we understand? We would see the eigenvalues. So if the eigenvalue is nearly 0, that means we can ignore that eigenvector or principal component. So each eigenvector is a principal component. Is that clear? But if you read a little bit, you can just easily understand. If you consider this, that okay, we subtract the mean, we take the mean out and we apply the covariance, okay, from sample to sample, then we try to find out the eigenvalue decomposition, okay, then projection, that's it. So there are not many steps. So these are the principal bases, okay, from top to bottom. So as you can see here, there are so many principal components. But when you go down here, you can see it's almost, it means nothing. Okay? But on top, you can see that this has some average shapes, top. And these are almost noise. So you can see that. And this is the same. Here only 150 I have shown, but it will be around more. Okay, because it's 0, so I didn't go further. Okay, so that means you can see here, I can consider 50 principal components from here. So my original image, if that's 50 by 50, the 1 by 2500, when I project into that one, 50 by 2500, and that is transpose, and that will become just 50 dimensional without losing much information. Okay, so we can just reduce dimension using that one. So what are the steps? Steps are basically convert each image to a row vector, every image, find out the mean, extract the mean. Okay? Then find out the covariance matrix of the data, and then find out the eigenvalue decomposition. Look at the eigenvalues. If that's more than 0, consider that principal component as a basis. Okay? And then collect them and apply original image onto that. Just multiplication with the transpose. Then that will be dimensionally reduced with that one. So that's basically how we can apply principal component analysis on images, and also in the signals. But when you apply in the images, that means that you need to, when you visualize, then you need to again convert it to in the image to see how it looks like. Okay, so that's how you can apply. And the same thing also applied in the facial expression or face recognition. In terms of average silhouettes or shapes, just like the previous picture, you can see the average faces. Okay, and this is mostly common in any classification or feature extraction tasks if you see, especially when data is very high dimensional. Okay? If you just find out a little bit details, just search a little bit and you can easily find out that how it's applied. Okay? And if you have further question, you can ask me anytime. Okay? Then I'll try to help you. So that's basically a common tool to apply. Okay? Just find out the vectors and multiply. And that will be dimensionally reduced in another space and without losing much information. After PCA, there is another dimensional little reduction technique, that's linear discriminant analysis. But in PCA, you don't need to know the sample group. Class 1, class 2, you don't need to know. But here, it works on supervised things. That means each vector, you know the corresponding class. And then apply that. Similar kind of eigenvalue decomposition, but here, you know the class of that sample. But in PCA, you don't need to know. Just find out the mean, subtract the mean, find out the covariance matrix, and apply eigenvalue decomposition on that. And consider the eigenvectors. Then multiply them. And just, that's it. But here, the formula is to find out between class scatter matrix and within class scatter matrix. Okay? So it's basically trying to minimize the variance of the samples in each class, inside the class, and trying to maximize the scatterness between the class. Simple. Okay? So this is the form, this is the scatter matrix with between class. Okay? You can see mean, total mean, and the specific mean. So find out the mean and then just find out the scatterness using the formula. And this is basically within the matrix, within the class, scatterness. So the target is to find out try to minimize this matrix, the scatterness within. Okay, for example, you can see here that we have two different groups here. Okay. So SW is basically trying to minimize the scatterness in between the samples of each class. Okay, and SB means the scatterness between the classes. So find out the maximization of this in between classes, this guy. So that's basically how LDA works. That means just a similar to this one, you can do just eigenvalue decomposition on this one. SW inverse SB. So find out these two matrices, multiply them, and find out the eigenvalue decomposition. And project that. That will be okay. Again, this is also very much used. You just do a little bit search and easily available in any kind of code. So, and that will find out the linear space. So when we have this binary sealers, and when we apply the LDA on that, and this is the class specific, so it knows which sample it belongs to, class, and it will try to find out some groups. Okay? So you can get a good cluster of samples over here. But in PCA, it's very difficult to show because you don't know the class, and you need to consider more principal components, and you cannot go beyond 3 dimension. But that doesn't mean that PCA works bad, but you have to consider more principal components over there. And in LDA, you don't have to consider that much principal components. If you have 6 classes, then you can reduce it to dimension 5. Okay? Because you can come up with rank 5. But if the data is not separable linearly, because this is linear discriminant analysis, right? LDA. But there is another technique to find out the data in non-linear space. In that case, you need to apply kernel. So on the original data, you apply it to the Gaussian kernel, okay? Then you apply this linear discriminant analysis. So based on the characteristics of this kernel function, you can find a hyperplane where you can separate the samples. So that's called GDA, okay? You can also apply generalized discriminant analysis. And there are other variations. So once you apply this LDA, other things are just a little bit variations and the kernel trick to find out the appropriate classification techniques. And it's just based on the data, how your data is organized. Then which techniques you can apply, and you can see how it works. So for dimension reduction, you can apply PCA, you can apply LDA, or you can apply GDA, or there is also QDA, okay? So they are just a little bit variance, a little bit the change of these things. Then in signal processing and also in image processing tasks, there is another feature extraction technique that's called independent component analysis, which was really famous some years ago. So it's basically not like principal component analysis. It says that, okay, the basis images or the basis things, okay, basis vectors or principal components, they might not be orthogonal to each other. Okay, then let's try to find out the independent vectors which are not related to each other and try to find out the space and get the data projected onto that. So this can be used in various things like noise removal, okay, and find out the local features in phase, in shapes, in other techniques. So this was quite interesting that if you have multiple microphones, 2 microphones, and you have 2 sources, so if you can find out the observations, okay, from the same number of sources, then just have this data from the observation. You will find out the sources. If 2 people are talking and I have 2 microphones, I just have the microphone data, okay? If I apply ICA, of course it's a little bit complicated algorithms happening inside that, to find if I will try to find out the independent sources inside the observation so that I can find out the original source. So ICA basically targets to find out the independent sources. So that was the main focus when ICA is applied. So it's basically, it says that if X is the observation, there must be some matrix, mixing matrix, that we can multiply with the original source, okay, to get the observation. Now we only have the observation, right? We only have the microphone data, and we don't have the original sources. So this is the technique that you can just find out some kind of independence, okay, on the sources and mixing matrix. So basically we will focus on X and then try to find out some matrix that can generate independent sources. Because we only have X. We don't have this S. So this is basically trying to find out some independent sources so that we can apply some feature extraction technique. For example, we have some ECG signals, HARP. Okay, so we are collecting based on the electrode. We are collecting some signals. Now those signals may have noises, right? Okay, so we only have the data. We don't have the sources, the noise coming from. So if we analyze, we can find out the different independent sources, and those signals we can compare with the noise characteristics and then remove them. So by that way, you can also remove noises from the observation. So this has a kind of vast applications in image processing and signal processing like that. So you can see here that there are 2 observations So that's believed that that's basically collection of the linear combination of these two original sources. Okay? So the target is to find out the mixing matrix that can be mixed with these original sources. Okay? To find out this original, characteristics of the signals. Again, how can we apply for noise removal? We can just remove the IC and then reconstruct. Okay? We have original data. We have independent components, just like principal components, and see which independent component we need to consider and which not. If we don't have to consider, we can just put it 0 and then reconstruct. Then the reconstructed signal would be noise removed. So that's basically how ICA is applied over here. So as I told you that here, X1, this is the observation that we have, but we don't have this S1 and S2. We are trying to have. Okay? And that was possible. That was done. So it was quite interesting, especially in speech processing. Okay? To find out the different sounds from the microphones. It was applied. So that's basically kind of like that. So you have mixed signals. Okay? Try to find out a linear combination of this space and then rotate that so that we can find some original source. And there is fixed point algorithm. As I said, that try random weight and then try to mix it and update it and find out the non-Gaussianality as non-Gaussianality is considered as independent signals from each other when we can apply. And in image processing, what I did basically, I applied PCA first to reduce the dimension, and then applied ICA on the principal components or eigenvectors, so that we can get independent components on the pieces. Because those has the original, most of the information hidden inside that eigenvectors. So basic steps of IC is just collect the data matrix, do some wiping process, and then again eigenvectors and values, and then try to adjust the weight until you find out non-correlated sources. Okay, that's the main characteristics of ICA. So that the components, they are independent of each other. Then we can consider that as independent source. So try to adjust the weight again and again like that. So when we have some phase images, if we apply independent component analysis, you can see here that PCA was kind of average things. Okay? Here you can have some locally focused images. If we apply it on image. Okay? You can see somewhere lips are focused, eyes are focused, eyebrows are focused like that. So, ICA in computer vision is basically applied to find out locally independent components, and they represent local features in the image. PCA in image processing things focuses on global features like average. But when you apply independent component analysis on faces or shapes or any image processing thing, it will find out the locally important features. Okay? And it's easy to implement. There is available codes. You just search fast ICA and you can get easily available, and it's downloadable free of cost. So if we apply ICA on these body shapes, we can get some locally focused images like this, leg, hand, like that. Okay? If we try to apply dimension reduction and as well as locally important features, then PCA is applied first. Try to find out the principal components, then apply ICA on the principal components to get the local features. So we can project into PCA first, then the projected PCA features we can apply to ICA. So in that way we can reduce the dimension and also we can find out the locally important features. So that's how you can go if your research matches with these things, you can do. And if your research matches with the signal processing things, so you can apply independent component analysis on the observation signals, find out the independent sources. If your target is to noise removal, then try to find out the independent sources that has relation with the noise and just remove it. So you can remove it by making them zero and then reconstruct the reverse projection, reconstruct action. Then the original signal will be noise removed. Okay, so these are basically finding out some features. So I'm giving you quick information about this, and if you have more interest, you can just ask me later on. And then the next feature is optical flows. That's basically motion features, and that's applied in video. Okay, just to find out a pixel in one frame, where is that in the next frame? That's it. For example, a person is running. I have a behavior recognition thing. So if a person is walking, then you can see that the pixels are moving, right? Okay. So optical flows is basically, it tries to find out the flow of the pixel in the next frame. Okay. Now, how to find out the flow? That's the important. You can compare the intensity of the pixel, or you can compare the block. Where is that block in the next frame? And that's basically optical flow. So there are several techniques you can apply on that one. So you can see a sample example. This is for kind of walking in 2 frames, consecutive frames. You can see that flow is not that big, because when you walk, it doesn't change that much. Okay? But when you run, so you can see here that it's a little bit. So this is not the image, this is flow, vector. And this is plotted by the quiver command in MATLAB. So you can try it. So that basically draws the vector. So this is basically vector, not and represented from 2 consecutive frames of behavior. This is from walking, and this is from running. So by seeing that, you can understand that 2 activities, they are different. That means it can get a good feature if you want to separate one class from another class. Okay, that's basically optical. And there are several techniques like Lucas Canale, so you can just search it, and you can apply those features with, again, LDA. Okay, first apply optical flows, and then you can apply LDA or GDA, and you can see that the samples, they are clustered together. So you can see here that walking, this color, they are together, right? Because they belong to the same class. Do you understand? So this is basically 3D plot of the optical flows of the frames, consecutive frames. So you can see that they are clustered together. Is that understood a little bit? I think. Okay.
How do you compute the pixel's next position?
And that's what I'm saying. There are several techniques.
Okay.
You can find out that, okay, same intensity, the pixels have some values, right? So where is the same value in the near about in the next frame? Now you can say that, okay, there are 5 pixels that has the same value. Then which one is that? Right? Because the regions, they have the similar values. Okay, if you convert it to the grayscale, averaging RGB, okay, then you can see that the same pixel, if you consider find out the same pixel in the next frame, you will find out the near, right? But it may have the same value. That's why there are several techniques. You can find out the block, surrounded block. A pixel, for example, for a pixel, you can find out the 9 pixels or 10 pixels in the same block and try to find out the same block in the next frame, near around. So it's basically finding out the correspondence. in the next frame. And just calculate the motion in x direction, in y direction, and also the magnitude. Do you understand here? I think I'll draw a little bit out here. This is the pixel. This is an image. The pixel is here. Okay. For example, this is a face image, for example, or smiling here, little wide. Okay. For example, this is a pixel over here. Now, while it's smiling, maybe this pixel comes over here. Okay. So it's basically trying to find out the pixel in the next frame. Okay. This pixel from here, it goes to here. So how much it moved in the next frame, how much previously it was here, now it's here. So how much it moved to x direction, how much it moved to the y direction, row and column. And then what was the magnitude, the resultant of this x and y, of the direction. So these three things you can represent the features. Okay? So, and see the vector, how it moved. So that's what I draw here. So this is the basically vector. That means this pixel moved here in the next frame. So that was the vector, which direction it moved. If you enlarge this image, you can see an arrow. So this is basically minimized, small. If you just make it big, you can see a vector. So this is a quiver comment. So you can apply that and you can see the arrows, which way the pixel moved. Okay, that's basically you can find out that. So it's basically finding out the correspondence. A pixel, where is that in the next image? Definitely it would not be very far away. So try to find out that in the nearby. If multiple pixels has the same value, then you will find out the block. A block, where is that in the next one? And the whole block moved in some distance, and you can just represent that. And the next basic feature extraction for image processing is local binary pattern. This is very simple feature based on the pixel value. Just, for example, this one. If the side value, if the surrounding values, if they are greater than the central pixel, then you represent 1. If less than the central pixel, you represent 0, like this. Okay? See, 101 is greater than 41. So this is 1. Okay? Then you can see here 26 is less than 0. So you have 8 bits for each pixel. Then organize the 8 bits. So you can see here that 1, 1, 1, 1, 0, like this from here. 1, 1, 0, 1, 1, 1, 1, 0. So 8-bit pattern. The direction which way you would go, that's up to you. Clockwise, anti-clockwise, or from where to where. So LBP features is basically find out the pattern, local binary pattern, and then find out the histogram. You understand the histogram, right? The frequency of that value. In the whole image or in the some blocks. So that's basically local binary pattern. Find out a binary pattern and find out the corresponding decimal number for that one and find out the histogram for that one. That's basically local binary pattern. Should we have some break now? What do you say? Okay, let's have some break then.